Jamen, jeg tror, vi sådan stille og roligt går i gang. Det bliver en eksklusiv lille flok. Men det er i hvert fald dejligt at se alle jer, der er kommet. Eller ikke se jer, men i hvert fald at høre jer. På vegne af DNNK, så vil jeg rigtig gerne byde jer alle sammen velkommen til denne her Tech Talk. Og Tech Talk, det er jo en af DNNK's formidlingsplatforme, hvor i at producenter, videnspartnere kan komme og præsentere deres produkt og fortælle lidt om, hvordan netop deres produkt eller netop deres viden kan bidrage ind i klimatilpasning. I dag der skal vi høre Dan og Anders fra Lapinus fortælle om deres produkt, der hedder Rockflow. Og Rockflow adresserer en af de her rigtig altid tilstedeværende problemstillinger i klimatilpasningsløsningerne, nemlig hvordan får vi plads til mest mulig vand på mindst mulig plads. Og det er jeg helt sikker på, at Dan vil komme videre og nærmere ind på. Programmet er for i dag, det er, at der kommer først en kort intro fra DNNK, det er mig, Theis, og jeg er snart færdig. Herefter så kommer Dan på i cirka en lille halv time med hans oplæg. Oplægget vil være på engelsk, men spørgsmål med videre både i chatten, og hvis man har nogen, dem kan man bare skrive på dansk, det er ikke noget problem. Og så slutter vi af med cirka 10 minutters tid til spørgsmål og uddybning. Så I skal endelig ikke holde jer tilbage. Og I skriver bare jeres spørgsmål i chatten, så skal jeg nok løbende få samlet sammen med Anders, og så tager vi dem op her til slut. Og ellers det tror jeg egentlig, det var det for mig. Jo, jeg kan lige kort sige, at TikTok'en bliver selvfølgelig også optaget, og det vil sige, at den kommer til også at ligge på DNNK's hjemmeside. Så hvis der lige er noget, man misser i løbet af præsentationen, så kan man altid gå tilbage til hjemmesiden og så se den igen. Ellers så tror jeg egentlig bare, at jeg vil overlade ordet til dig, Dan, og din præsentation.
Super, tak. Thank you for joining this talk. I do speak Danish, but to give a tech talk in Danish is a little bit of a challenge. My name is Dan de Kubber. I'm within Rockwool responsible for the Innovation and Development Department that is running the Urban Climate Adaptation program. Today I would like to show you why we are working on new products, why we are working on urban climate adaptation, and how it's connected to the new requirements in the market that are a result of a changing world. Yes. So a changing world, it has many aspects, of course. I want to highlight two of them. The first one being the urbanization, where we see over the last 50 years, for instance, that 23% of the people, more people are living in cities in Europe. If I look specifically at Denmark, then in 2019 already 88% of the Danish population was living in cities. And looking ahead, then we foresee that by 2030 there's already 39 megacities in the world with more than 10 million people. I'm not sure if that will happen in Denmark, but for sure it's a very clear trend of more people moving to the cities. This has some important impacts. For instance, above ground, we see more and more hard surfaces, and all the rainwater falling on those surfaces are traditionally guided out of the city as quickly as possible. Below ground, we see equally busy streets with a lot of pipes and cables, some of them already there for 150 years. And I think you can see a very crowded space both below and above ground in these cities. Next to that, we have the climate change. Just to give some numbers on that, over the last 40 years, there has been an 83% increase of extreme weather events. And extreme weather events can be droughts, like we see in California and the Mediterranean, Australia, but also more and more heavy storms that we have seen. Like, for instance, the cloudburst that was there in Denmark 10 years ago. Over a period of 10 years, we've seen 3.4 million people in Europe only affected by floods. So it is a big and increasing problem. In Denmark specifically, over the last 150 years, we've seen a 15% increase of precipitation. So what does that mean for the changing world in the urban setting with regards to urban climate adaptation? For one, there's too much water. As I've said, 15% increase in absolute precipitation, but definitely also an increase in the extreme weather events, so the cloudbursts. In between those cloudbursts, we see there's too little water, leading to drought periods in between the rain events. But also another aspect of the too little water is that all the rain that is falling is channeled out of the city, meaning that let's say the precious resource that water is not retained, and you see, for instance, a lot of big cities that are subsiding, and so the ground level is lowering in time. And this goes actually faster for those cities than the seawater level is rising. So that definitely is also a very important aspect. And it's too hot. You have the urban heat island effect. It is caused by a lot of hard reflecting surfaces in the city. So all the heat by the sun is kept inside the city. Another important aspect is that through the years we did not think in the past that it is worthwhile to have a lot of green and water inside the city, but evapotranspiration from trees is actually a very effective means to lower this temperature. But as there is very limited green, we see this heat island effect. Space constraints. As well above as well as below ground, we have very little space in the city. We value the space very high, so we try to get the maximum out of every square meter inside cities for habitation, for the streets, cars. So there's very little space left to do anything about urban climate. Then the last point, sustainability. Of course, the solutions that we implement now, we don't want them to have a negative effect and make the problem only worse in the future. So we want to use as much as possible natural materials and also use them in a way that they don't disturb the environment too much. All these aspects, they are captured in a framework of legislation within Europe. There's this overview. First of all, we have the Water Framework Directive. Sorry, it has been there since 2000, and it is set in place to improve the water quality of the groundwater and all the surface waters. And also to mitigate the effects of floodings and droughts. So it's a very basic directive that sets constraints to what countries and cities can do with regards to water. I think a very important aspect of this part of the legislation is the demands that is set on the ecological and chemical health or quality, as you want, of the surface waters. Then another very important one on the lower right corner is the Urban Wastewater Treatment Directive. It has been alive since 1991, so it's a very old one, but still very active. And it has the objective to prevent environmental pollution by sewage water runoffs. So basically it says by insufficient treatment of wastewater. But what happens a lot is that sewage water enters the environment untreated, and it gives a very big negative impact on the quality of the water. Last but not least, there is the Flutter Directive. It's the relatively newest directive. It's from 2007. And that specifically looks at the adverse effects on the environment of floodings. It does not specifically look at floods from stormwater from cloudburst. It is believed that probably this year there will be a renewal of these three legislative frameworks, and it is believed that the Flood Directive will specifically say something about stormwater. This Flood Directive enforces all the member states to have flood risk management plans, which tells something about how is a city going to prevent floodings. And they're typically in what you see in Denmark and also in the Netherlands, and you see that now more and more in other European countries. These flood risk management plans do not only look at rivers, but definitely also look at the stormwater. So all in all, this framework of European legislation aims to, for one, make sure that water gets cleaner and cleaner. So specifically looking at the groundwater and the surface water. Secondly, getting these waters cleaner requires preventing overruns from the sewer system towards the environment. And thirdly, you can prevent these overflows of the sewer system by preventing rainwater coming into the dirt water sewer. So these three legislations, they give a very good framework of how we can handle this problem. So how big is the problem? If I look at Denmark, then for sure there is a lot of overflows of the sewer systems. This map on the right is made by the data from the Filtration. It was published last year. I believe it's data from 2019. And I know the map is very much disputed because it's based on calculations and not on actual measurements of overflows. But it does indicate that the number of overflows is very substantial, and it's throughout the whole country. Maybe concentrated in Copenhagen if I look at the colors, but the problem basically is everywhere. So what should we do? One solution that has been traditionally used is to install pipes, big pipes, sewer pipes to capture all the dirt water and the rainwater, and then bring it to the wastewater treatment plant and get rid of it. But we see with the bigger rains that you would need even bigger pipes than you already have. And then if you install a big pipe in one street, then the water going to the next street will be even more, so you need an even bigger pipe there. And it's a cascade of problems, and you would need ever bigger pipes. This is both very expensive, almost prohibitively expensive, but next to that, you would also throw out all the water that you very well need inside the cities for the urban heat island effect, but also for the too little water problem, which can give in the end soil subsidence. So we preach more to keep the water local, the rainwater local, capture it into systems, buffers, creeks, bodies, all kinds of SOTS systems. But then also we need to clean that water before it's sent to a recipient to make sure that we fulfill these demands or start fulfilling the demands of chemical and ecological quality. So what kind of solutions could be used? First, on the left, we have the nature-based solutions, which I would say should always be preferred if possible. So having the water above ground has a lot of benefits, both in terms of costs. It's a very cheap solution, but also the water in the environment gives a lot of benefits for the people living there, for the green, but also for the aesthetical aspects. Typically, you would have these kind of swales or wadis. And the water can be cleaned by the soil underneath. You have precipitation, of course, and you have a sand passage. Also in this category, I would say you have retention ponds that are used to clean rainwater already. I think these solutions are very effective and should be preferred, but in the urban setting, there's a lot of times you have space constraints, and you just don't have the space to use these natural-based solutions. Then you have the buffer solutions, which basically is a very large area where you can store water under the ground. That can be typically parking lots, industrial areas, all kinds of areas. You have these large buffer solutions. From there, the rainwater that is collected in it can infiltrate in the ground if it's clean enough, or typically you would also have a delayed discharge towards the sewer. So then at least you take out the peak in the water from a cloudburst, for instance. You take the peak off. You don't overload the sewer system, and you will not have sewer overruns. So it's a very effective solution for that. But again, you don't always have the space, and you don't always make the maximum use of the water. I think the urban green solutions, where we store the water very close to trees and urban green, you actually do make very efficient use of the water that is collected. It is transferred to the trees, for instance, from where it evapotranspirates, which lowers the temperature, albeit that effect typically is very local. So you don't solve the heat island effect of a complete city, but if you can already reduce the temperatures and the comfort, increase the comfort in a street, is already a really big win. Disadvantage of these systems is that you cannot store large amounts of water. So then you would have to combine it with one of the other systems. The last system where we as Rockflow work very much on is the stormwater sewer system. So it's a parallel system to the dirt water sewer. All the rainwater and the storm events, they can be stored very quickly into this stormwater sewer or infiltration sewer. And from there, it can infiltrate slowly into the ground, or again, if necessary, you could have a delayed discharge to the sewer system, to the dirt water sewer system. So what is Rockflow? We make elements of stone wool that you might know from the insulation, rock wool insulation. Visually, it looks very similar. In practice, it's very different, where rock wool insulation is made to repel water. We have made Rockflow to absorb water, and it can do that very efficiently. We can absorb up to 95% of the volume of a stone wool block of water, and keep that there until the surroundings is ready to take up water again. We don't have any loss of, or minimal loss of urban space, I would say. We can install the Rockflow systems under streets, under parking lots, so the city above the system can just continue to run. It's a very flexible design. The stone wool can be cut very easily with simple tools into all kinds of shapes, and by that we can very easily work around all the pipes and cables that are existing in the subsoil. It's a sustainable material. The stone wool is made of volcanic rock, typically basalt, diabase. So the earth can produce much more of this rock, or is producing much more of this rock than we will ever be able to consume. So in that way, it's very sustainable raw material. Of course, we still use a lot of energy to melt the stone and make it into stone wool. Traditionally, that has always been done with carbon-based fuels, but Rockwool has now set a very ambitious goal to get away from the carbon-based fuels in the coming years. And the first steps have already been made. The first cupola oven in Denmark has been transferred last year to a biogas installation, which now runs completely CO2 neutral. We have the first large-scale electric melter in Moss in Norway, which will also run neutral, CO2 neutral. And that is 2 out of probably 30 or 40 factories that we have in the group. So we have a long way to go, yes, but I think we are very well on the right track there. Last but not least, and that is also why I want to have this talk here now today, is the filtration. What we saw very early when we started with Rockflow is that the pore size of the stone wool is very small, which means that we take out a lot of the suspended solids out of the system, out of the water. What we didn't know at that time is that we can also take a lot of dissolved pollutants out of the water. So that is also a little bit the basis of the rest of this talk. Rockflow, where have we installed it? We have installed over 160 projects over the last 3 years, I would say. We started in the Netherlands, where I'm from myself. So we have a very dense network of projects there already. Anders, also present in this talk, has been active in Denmark and doing a number of projects there. And we've also done some excursions to Sweden and Norway so far. The projects, they are really different in size and application. I think in the upper right corner you see a Vejbil, which is a smaller application inside the city of Copenhagen, I believe in this case. We have projects like large buffers in the middle, where there's a couple of hundreds of cubic meters installed in one area. And in the lower right corner you see an example of this rainwater sewer, where the rain of a complete neighborhood is collected under the street. The system is running parallel to the dirt water sewer. It's not visible anymore in this picture, it's just a little bit lower below ground. But a system like this, Rockflow, is running over 3 kilometers now in this one city. So very different kinds of projects that we have. Why is there a need for filtration? I said in the legislation, European legislation, it's already indicated that we should look after our waters, make sure that the quality is improving. And I think that this is a picture, I believe it's Koksø in Denmark, where you see a lot of eutrophication already of the lake here, meaning there's too many nutrients in the water, which leads to algae bloom, which gives a very poor biodiversity in the water. To prevent this, to remediate this, we need to make sure that all the water that is running from the city into this lake is cleaned of all the copper, zinc that is coming from the roofs, all the fertilizers that we've put on the lawn, all the fertilizers that comes down with the rain due to evaporation somewhere else. So it's important to clean this water that is running into the lake, to make sure that in time the quality of the water in the lake itself is also improved. So what did we do in the early stages? When we realized filtration is very important, we started testing. Here on the left side you see a test that we have been doing with TI in Denmark, where we specifically looked at the suspended solids. What you see is a channel going into the stone wool that we typically use to bring the water to our system. And what you see is that by far the most the suspended solids, they are captured within this channel. So we've done these tests to look at how much can we capture, which particles would come through if they do, where do they come through, what is the impact on the hydraulics of the system if you have this layer of suspended solids inside the channel, etc., etc. Then on the right hand side we took a different approach. We did this investigation with Wageningen University in the Netherlands, and there we looked specifically at the dissolved pollutants. So not so much the suspended particles, but the dissolved ones. And these tests are aimed at measuring the metals. So we added zinc, copper to the water, brought it into contact with stone wool, and measured how much of the copper is absorbed in the stone wool. We did the same with polyaromatic carbohydrates, pH, and also there measured how much of the dissolved organics can we take out. So this is a table of results we've gathered so far in different investigations. So in the lower right corner it says here TI and University of Wageningen. Some of these results are also captured in field tests, where we have installed actual systems in the field and measured the results there. Suspended solids. So in the first two columns you see the typical concentrations we see in runoff water. For suspended solids, typically around 90, but they can vary very much from 30 milligrams per liter very clean water to 300 milligrams per liter, which is very turbid water, I would say. We see in the performance that we take out over 94% of these suspended solids. And the chemical biological oxygen demand, so which is a measure for the amount of organics that we take out. There we also see a very large decrease of the COD, BOD in the effluent. Total phosphor, we're also quite efficient in taking it out, and that is because phosphates and all the structures that phosphate is part of, they typically tend to absorb to the suspended solids. So if you take out suspended solids, you already take out a lot of the phosphates. Same holds for nitrogen, where we can take out a lot of the nitrogen because they are absorbed to the suspended solids. The downside, what we saw, is that the dissolved phosphate absorbs very poorly to the stone wool as it is now. In the lower table, the table is split because you talk about a different order of magnitude. Instead of milligrams, we now talk about micrograms. I would say all the components, the heavy metals, copper, zinc, and also the PDHs, they are absorbed quite efficiently, not always to over 90%, but still quite efficiently out of the water. Now, one of those field tests, this is the project in Aarhus. It was code-named Underground. And it was installed in 2016 with the help of the MUDP program, subsidizing program. The idea here was to see if we can take these principles of filtration of stone wool and see if we can clean the water quality to a level equal to the present BAT. And the best available technology at this moment is the retention ponds that are used. They take up a lot of space, which would not be possible in this area in Aarhus, but they are very efficient in cleaning the water. If I go through very simply through the design, then here you have the entrance well that takes all the water that is coming from the cross-section area with the O2 ring in Aarhus. So there's a lot of water and a lot of polluted water, I would say also. From there it runs into a manifold where the water is distributed over different strings into the stone wool. In this case, we let the water run in from the top, and from there it slowly percolates to the bottom, and in the bottom it's collected again into a new well. And from that well, you would see here in the lower right picture in the end, from that well it runs into a number of swales that slowly go down to the fjord in Aarhus, if it's not infiltrated along the way. So I said we make sure the water runs in from the top here to get an optimal filtration. In a lot of other systems that we build for very speedy storm water or cloudburst applications, we would do it the other way around. We would fill from the bottom and push the air out from the top to get a faster filling. speed in this filtration is not the criterion efficient filtration is. So of course on the system, as we had the intention to see if we are better than bad or comparable to bad, we did a lot of measurements and compared them to the performance, the documented performance of the best available technology, the retention plant. The bullets here on the right hand side, the green bullets, they indicate that we have a performance better than BAT. The other ones where we are comparable to BAT, and the red one is where we underperform compared to the BAT. As you can see along the line, we have a good performance. We just have a problem with the phosphates. Then, luckily, we were able to talk to Ole Larsen, which you probably, most of you will know, also part of the DNNK network. And he brought us on the track of looking at iron oxides. The first questions that we try to answer together with Ole Larsen is, can we grow iron oxides on the wool, and by that have a huge increase in surface area, and can this iron oxide in the wool also capture phosphates? So that has been the topic of investigation for the last half year, I would say. And here is some of the results, just to temper the expectations. We don't have a product yet. We are still developing, but here is the result we have so far. So this is on the left hand side, let's say naked stone wool as it comes out of our production. And then in the middle you see the product after it has been coated with iron oxide. And the iron coating is through and through, and that you can see on the right hand side, the microscopic picture, where all the glassy fibers are actually stone wool fibers, and now the pink reddish dots is iron oxide grown on top of the fibers. And this has increased the surface area of the samples enormously. We don't have results of our own laboratory yet, which we are gathering as we speak. I believe our laborant is measuring phosphate concentrations today. But these are the results of Ole, where you see the sorption capacity of different ways of applying, after different ways of applying the iron oxide coating on the wool. The reference here has a sorption capacity of 1. It's all relative numbers of 1, and then you see in some of the treatments that Ole did, we get a 480 times higher sorption capacity of phosphate on the wool than the naked wool. So of course this is a path we want to continue to look at. So what are the next steps for us? First of all, making a sample in the lab is very different than making it full scale. Rock wool production lines, they produce maybe 10,000 kilograms of stone wool per hour, and having a iron oxide coating process in that production process will be a big challenge. So of course that is one of the things that we look at very much at this moment. How can we mimic, or how can we copy this production process in real life? Then secondly, what is the sorption efficiency of those phosphates? If we have those two answers, we could come with a, let's say, preliminary product that we can start testing. But before we really are able to have a commercial product, we need to look more into details at the filter design. How should we design it? For instance, this example you see here on the picture is a project we did in Bovense on Funen, where we managed to make a very efficient filter, but we kind of made some mistakes with the hydraulics. So it's working very well as a filter, but not so much as a buffer. So some work to be done on a filter design where we will improve. Next to that, we need documentation. Of course, we need to show with data from labs, but also from real life, how we can capture this phosphate. Maybe there's also other components we will look at in the future. And then last but not least, experience. We need to build up experience before to get to a real commercial product. So getting back to the larger perspective, what we want to do as Rockflow is provide tools for the people in the market to handle this urban climate adaptation. We see there are ways to address the too much, the too little, and the too hot aspects of urban climate adaptation within the space constraints of a city and within the sustainability aspects that are set. We want to have a minimal negative impact. That is also, of course, why within our production we are looking at carbon zero based production methods, but we also want to maximize our positive impact on the environment. I hope with the developments that we are doing at this moment, have been doing in the past and are doing at this moment, we can contribute to the challenges that we see in the urban climate adaptation. Thank you very much for your attention, and I'm really eager to see if there's any questions.
Yeah, thank you so much, Dan. It was a great talk, and I think we'll switch to Danish if it's okay with you.
Definitely, yes.
Katrine har et spørgsmål, og I andre, I skal jo bare stille et spørgsmål, så bliver de håndteret løbende. Katrine har et spørgsmål, som hedder, hvor længe regner I med, at Rockflow bevarer sin renseeffekt? Hvor længe skal vandet stå i batchen?
Hvad er levetiden af en filter for den del af fosfat? Det ved jeg ikke endnu. Der er alt for meget, vi skal finde ud af. Hvis jeg kigger på den almindelige filter, så er der de suspended solids, som vi fanger ind i indløbskanaler, som kan renses. Så den levetid af den type filter vil være, det ved jeg heller ikke, vi er på gang nu i 3-4 år, men vi forventer, at det ikke er noget problem at få en levetid på 40-50 years. Ja.
Super. Så er der et andet spørgsmål fra Karina. Har I testet levetiden på de her rock-uldspaneler? Kræver de oprensning?
Selvfølgelig der er en maintenance, en vedligeholdelse, man skal have. Og så hvis man følger den vedligeholdelse og inspicerer systemet, når det er nødvendigt, og rense, når det er nødvendigt, så kan man nemt komme op til en meget langt levetid. Måske Anders, har du noget andet?
Jeg ved ikke, går jeg igennem?
Ja.
Ja, det er fint. Altså igen, som Dan siger, så i forhold til levetiden af de almindelige elementer, så i det der ikke kommer noget sediment ud i matrisen af stenulden, så hvis man kan rense eller bygge sit anlæg, så man kan komme ind og rense de her indløbskanaler, så er levetiden den levetid, der er for ulden, og den er minimum 50 år. Og det samme gælder sådan set også for vores filter, som Dan sagde, altså suspenderet stof, det handler om, at man kan rense den her indløbskanal. Og så er der hvis man også har indbygget kapacitet til at tage noget hydraulisk opsamling, så vil tilbageholdelse af opløste stoffer være mange gange større end det, der er brug for i et pågældende opland. Men det er altså noget, vi gerne hjælper med i forhold til et konkret projekt, også estimere levetid af.
Tusind tak for svaret. Mens I andre lige tænker over andre spørgsmål, så har jeg også et. Jeg kunne godt tænke mig at høre, du nævnte kort, Dan, at næste skridt i udviklingen var at få kombineret, prøve at kigge, om I kan komme af med fosfaten ved at lave forskellige løsninger. Ja. Har I andre udviklingstanker? Altså for eksempel, har I overvejet om, hvordan kan I kombinere denne her løsning med andre løsninger, og har I erfaringer for det?
Vi har tanker. Problemet der er, at vi ikke ved helt præcis endnu, hvad kinetikken er på den fosfatrensning. Så vi ved ikke, om vi skal have en langt eller kort vedligeholdelsestid ind i filteret. Og det vil være meget afgørende af, hvordan filteret skal se ud, og hvor vi kan kombinere det med andre systemer. Er det et svar?
Ja, tusind tak skal du have.
Ja.
Jeg har endnu et spørgsmål. Jeg skal høre, med hensyn til medier, altså jeg tænker planter og des videre, har I nogle erfaringer med, om jeres løsning, Rockflow, kan kombineres med plantevækst med videre?
Ja, selvfølgelig har vi en datterselskab i Rockwool, som hedder Godan, hvor vi vokser planter på stenud. Så det kan godt lade sig gøre, men i drivhusser, hvor det bliver brugt, der har de meget stor kontrol over den vand, som kommer ind i stenud. Så der er alle næringsstoffer, de er inde i vand, og der findes ikke noget næringsstoffer inde i stenud. Så hvis du gerne vil gøre det ud i byer, så plejer det at være en løsning, hvor stenud sørger for en vandbalance, hvor vi capturer alt muligt vand eller regnvand og frigiver det til et substrat, hvor planter vokser i. Fordi der kommer ikke noget nutrienter ud af vores stenud.
Tusind tak, Dan. Her til sidst så vil jeg høre, om der er nogen, der har et spørgsmål her på falderebet til Dan eller Anders. Og det tror jeg ikke. Ellers kan I altid tage fat i dem, uafhængigt af DNNK. Ellers så vil jeg sige tusind tak, Dan, og tusind tak, Anders, for jeres rigtig spændende præsentation. Det var rigtig spændende at høre om jeres produkt. Der er helt sikkert et kæmpe potentiale for det. Og ellers så vil jeg på vegne af DNK sige tak, både til deltagerne og til Dan og Anders. Og som sagt, så kan I finde en optagelse af denne her Tech Talk inde på DNNK's hjemmeside. Og inde på DNNK kan I også orientere jer om kommende Tech Talks. Så på vegne af DNK, så vil jeg sige tak til oplægsholdere og til jer, der lyttede med.
Mange tak.
Men tak.
Farvel.